Some native modules in Node.js are implemented in C++, which allows them to obviously run much faster than their plain JavaScript counterparts. Node comes in with a few of those modules built in. For example, the crypto module, which provides cryptographic functionality, including wrappers for OpenSSL's hash, HMAC, cipher, decipher, sign, and verify functions. Although it's implemented in C++, it offers a JavaScript API for easy usage. You might not be using all that often OpenSSL's method, but actually crypto comes in quite handy, especially when you are handling authentication, authorization, and stuff like that. Next, we've got the buffer. Node.js includes a buffer class for efficiently handling binary data. It is backed by raw memory outside of the V8 heap, and just like crypto, it's implemented in C++ with JavaScript bindings. And finally, possibly one of the most frequently used or most useful to a regular developer, stream module, which is also implemented in C++, and it handles streaming data in Node. It's particularly useful for I/O operations, providing a fast and efficient way to process your data streams via JavaScript. The next quite important and useful module for CPU-bound tasks is the worker threads. It allows you to run JavaScript code in separate threads outside of the main event loop and the main thread. This can significantly improve the performance of CPU-bound tasks and the overall application by enabling those tasks to be run in parallel with the main thread, preventing it from being blocked. Now, the worker threads are most powerful when you've got multiple requests requiring some computations and you don't want to block the application. Let's see how worker threads work in practice. So I'm here in my code editor. This is the course repo. I'm going to section 2 folder and let me find improving performance of CPU-bound tasks. Here we've got the child processes folder, that's for later, the util folder, worker threads, and the baseline. Let's open up the baseline. We're going to start here. So what we're going to try and do is to see whether using worker threads or child processes in a minute, whether that in fact improves the performance of our script. And what does the script do? We're going to be counting elements of a large array. Here we've got a utility function, which is going to create an array filled with letter A, 15 million instances of that letter. And then we're going to be counting those elements. And we're going to benchmark performance of this count elements function. All it does, it basically iterates over the entire thing. And each time it finds letter A, it's going to add 1 to the overall count. This is a very contrived example, but it will provide us with CPU-bound tasks, the one which we are considering in this lecture. Right, so in the baseline script, all we do at the end, we are basically outputting the count with the time in milliseconds it took the count elements function to complete. The important thing is to create the 50 million elements array before we start the timer, not to include this task in our script. Okay, let me open my terminal. Copy the relative path of this script. It took 340 milliseconds to count those 50 million elements. It serves as the benchmark. Now we know what this task takes when just being run in the main thread. Okay, so let's see if using worker threads would actually make any difference in this case. This is a file which is split into two sections. The first one starts with the if statement on line 4. It basically checks through the isMainThread facility from worker threads module whether we are in the main thread. If we are, then we're going to be creating this large array, and then we start the timer. We then create the worker thread, and we're going to output the amount of milliseconds it took the main thread to create this worker. This is an interesting exercise because it will give us the overhead of actually creating the worker itself. Then what we do, the array goes into that worker. And actually we could think about this as a tunnel going straight to this else section over here, starting on line 30. In here, we're gonna be listening on the parent port. And once it receives a message with our array, we're gonna start counting those elements after we've initiated another timer. This time we're gonna count how many milliseconds it took this separate thread to process the count. And this console log is gonna give us that information. And then finally on line 40, once the count is done, the console log is done, we are sending this count back to the main thread. On line 17, we are listening for that message coming with the count, and I am logging the count itself and the number of milliseconds it took this worker to receive the count. Another interesting console log is here on line 25. It will basically count the amount of milliseconds for which the main thread was blocked. And what was blocking this main thread was the action of sending the array into another thread. Okay, so again, let's copy this relative path, open this up, and let's run the script. And here are the results. First of all, the new worker was initiated in just 8 milliseconds, which is not that bad. Then another console log about the amount of time the main thread was blocked. That's over 2 seconds that the application was unresponsive. And those 2 seconds were basically the time between creating this worker and then sending the array into it. Then on this line, we see that the processing of the count took actually 300 milliseconds. If you remember the baseline over here, that was also about 300 milliseconds. So what we find is that the worker took pretty much the same, if not slightly shorter amount of time to perform the same task. And then we see the output from the final console log, which received the information back from the worker. So what conclusions can be drawn here? Well, first of all, the separate thread performed even better than the baseline. So that's great. What's not so great is the amount of time for which the main thread was blocked and the amount of time it took for the entire task to be completed. And this gives us the information back that even though we didn't block the main thread for the entirety of this task, we did block it for considerable time because we wanted to communicate with the worker. So probably a more performant way to do this would be to actually split the task into batches to avoid this excessive amount of time required to pass this large array in memory from one place to another or from one thread to another. And now child processes. Child process module in Node.js can create separate processes to execute tasks, allowing the application to utilize multiple CPU cores for improved performance. A child process runs in its own V8 instance and has its own memory space, which is advantageous for CPU-bound tasks as it ensures they won't block the main thread, just like the worker threads did. However, it's important to note that starting a child process involves more overhead compared to spinning up a new thread. You can observe this by running a simple code example to measure the overhead difference between child processes and worker threads. And that's exactly what we are gonna do now. Okay, let's close the worker threads example. Going into child processes. Two files in here. Index, which is the main thread file, if you will. So this will be executed in the main thread. And then we've got a child file. So this basically is going to run in a separate process altogether. So in this file, what we are doing, pretty much repeating the same stuff we did for the worker thread. We are initiating a timer, we are counting the elements, console logging the time it took to process the count, and then sending back the result. In the main file, I use the fork function from the child processes module to spin up a new node instance in a separate thread. Then I'm sending that large array into that separate thread. And as we did before, I'm logging the amount of time that the main thread is being blocked. And then once the child process sends the message back to the main thread, I'm console logging the amount of time with the count. And lastly, I'm killing that process to make sure I'm cleaning up the resources. Okay, so copying the relative path, let's open up the terminal. I'll leave the outputs from the previous runs here for comparisons, and let's run the script. Okay, so a few interesting results here. You'll notice that the child process got created in 3 milliseconds. That is actually much better than we did over here with worker threads. So it would seem that spinning up a new node process on my machine is actually more performant than spinning up a new worker thread. Second, the main thread got blocked for 3.5 seconds over here, which is considerably longer than in the case of child processes. Then counting of the large array took 300 milliseconds, which again is comparable both to the baseline and the worker thread. And finally, the total time it took to complete this task using child process took pretty much similar time to worker threads, just under 6 seconds. So the conclusion is here. It seems like child process on my machine is performing pretty much similar to worker threads. The one significant difference is the amount of time it took for the main thread to get unlocked in case of the worker threads and child process. If I repeat this task, let's see if that is any different. No, pretty much the same. So from this, we can gather that actually running child process is going to be more expensive for the main thread, as in it's going to block it for longer time and our application will be unresponsive in the main thread. So if we are to run any tasks in parallel, probably worker threads could be more performant in terms of allowing the rest of the application to run. Child processes obviously have their place, and we're going to talk about that later as well. But back to the main subject of improving performance of CPU-bound tasks. In extreme cases where the performance limitations of Node.js impact the entire business solution, you might consider migrating that part of your application to a different programming language altogether and deploying it as a separate microservice. Now, this approach can offer significant performance gains, but introduces network latency and increases the complexity of your system. It's a trade-off that should be carefully considered.